Okay, good morning, everyone. It's a pleasure to have Bruno Carvalho here with us today. So I'll briefly introduce him. Bruno did his PhD in physics from the Federal University of Minas Gerais, where he studied resonant Raman spectroscopy. And during his PhD, he spent a period as a researcher at Pennsylvania State University. For his postdoc, he went to Cornell University, where he focused on optical phenomena in 2D materials. And he's currently an associate professor here at the university, so it's a pleasure to have someone from the house. His research employs nanoscale optical techniques to investigate the behavior of electrons, phonons, and defects in two-dimensional materials. So Bruno, thank you for agreeing to be here, and the stage is yours.
Thank you so much, Marcia, for the introduction. Hello, everyone. So it's a pleasure to be here. It's been a while, honestly. So today we're talking about, maybe this title here is a little bit weird, talking about symmetry breaking here in the Institute, but symmetry breaking for me, which is from condensed matter, is just introducing something on a crystal and see what will happen. Basically, this is break the natural hosting materials, okay? And my goal today is basically trying to demonstrate you all that defects are not something, it's not a flaw to have if you can actually control them when you are introducing in a material. So today, I hope to actually bridge the gap between fundamental synthesis and applications using defects intentionally into the materials. Okay, so just a brief comment. Everything I'm going to mention here today, so it's basically involving those three works. Actually, I will mention 4 works. They are correlated between them. And I will be also, all the work I'm mentioning here is in collaboration with some, of course, Brazilian universities, especially UFMG, UFOP, and CNPEN, and also includes Penn State University and Japan and Korea as well. So everything is going to demonstrate in here is actually a network of collaborations in Brazil and also internationally. Usually, we see defects as something bad. And how actually I started to work with defects, it was actually 10 years ago. Actually, we will complete the publication of this paper. And it was in 2016. We didn't know much about defects at all. So we only saw that as actually imperfections. And those imperfections was something that we didn't want to have in our material. So this work, actually, I was a PhD candidate. It was well accepted. It has more than 80,000 downloads. And actually, let's see. Okay, I will keep it in my hands. Maybe it's better. And it was also, so it has more than 80K downloads and almost 1,000 citations since then. And something that actually, through this time, this period of time, through these 10 years, we actually got another paper published last year. I was invited by the APR. And this basically summarizes everything we got from using optical spectroscopy to unveil how defects actually change the material properties. However, during this review, we noticed there is a bottleneck. And the bottleneck is we know how to characterize defects. So we know how we can use light, and using light, basically try to get information about the system. However, we don't know how to control them. Is there a way how, instead of to have a random distribution of defects, is that a way to introduce it intentionally and control that and see what exactly I wanted to achieve by doing so? So this is actually what we are trying to do and what I'm going to try to demonstrate to you today. So, but what exactly is the fact? Okay, so the material I'm going to study for this defect engineering is basically some atoms, and these atoms are actually an intercalation between, I'm going to demonstrate later, but it's actually a transition metal like molybdenum, tungstenium, tantalum, and some chalcogenides. These chalcogenides usually are sulfide and selenium, basically. And interesting of these materials, they have, in the top view, they have this hexagon-like symmetry, basically. So a pristine sample means your host material is pure, is perfect, something like that. Of course, even in nature, that's not true because we have some imperfections, but they are not in higher concentration. And then one thing that we can do basically is try to have atomic vacancy. So we just remove some atoms and see what will happen. So there will be some vacancies. Another thing we can do, and this is what I'm going to demonstrate it today, is that we can remove one atom and put another one in place. And that will be done intentionally. All right. So we can also have some absorption materials that can be on the surface of the material as well, and also some kind of grain boundary, which should be something like this, as you can see here. Maybe it's not so clear, but the symmetry, it forms some kind of line, and this line we call it as one-dimensional defects. We can also have 2D. Just nowadays it's very common. You get two-dimensional materials like graphene, for instance, put on the top of each other, rotate, right? So we can have superconductivity, for instance. And what we are going to do is just to try to see as well if there is some change. This is considering a defect as well. So I will mainly focus on only one kind of defect, which is the substantial. So we will be replacing atoms by another one. So basically that's what I'm trying to do here. And how do we see these defects? This is some images we have from scan electronic transmission microscopy. So basically here we can see some vacancies. You can see there is some holes missing here. For instance, this is a very large area, so just for you can see that those holes are actually there. This is atomic imaging. So this is, for instance, not intentional. So some materials like CVD, which is materials that we grow in the lab, they can have this kind of structure, for instance. We can have some dopants over here, and we can also have some 80 atoms. This is what I mentioned by line defects that we can have along the sample, and as well some kind of grain boundaries. And even the edge of the material has some vacancies and some kind of features that is not perfect, actually. It's not a chain, a perfect like chain. So I will be focused today in dopants, basically. So I will be removing atoms and put another one in place intentionally. And the idea is try to see what exactly will happen with the electronic properties, with the vibrational properties, and see what kind of information we can get. So this is more like, yes.
Just a very naive question. So that's the panel E, what is vacancy in this?
Vacancy is just, for instance, you can see some holes here missing. Over here is missing one atom, another here there is missing another atom. So basically, if there is no vacancy here, it would be just like a perfect, like this one over here, which is a hexagonal symmetry. So that's it, basically. So this is natural, okay? So all materials in nature present like this. The only difference is that the concentration naturally is very few. It's very low, actually. So usually what we try to do is try to increase that somehow. So we can, I'm not going to show here, but we can actually do that by doing some kind of ion irradiation intentionally on the material. Okay. This is one of the works I also did. So actually, I have investigated all this kind of defects using different optical techniques. But to try to be a little bit more convincing that we can truly engineer defects, I'm going to show only one direction of the research. So just to emphasize, the material that I'm interested to is called transition metal dichalcogenides. And this is a 2D material family. So this has a very rich Welle physics, and this is important because all the materials that I'm studying here, they are semiconducting, okay? Except for graphene, that's another story, okay? So basically here is only a dispersion plot, so you can consider here just the energy as a function of K. And a semiconductor basically has this gap over here. You have the balancing band and the conduction band over here. So what is a valley? Valley basically means that we have the lower here in the conduction band and the maximum in the valence band. So when you have the same, they are here, you can see they have the same group velocity, we call this as a direct band gap. That's quite simple. Usually for semiconducting, the materials I'm studying here, this gap is in the visible range of energy. So it's variations between 1.9 electron volts to 2.2 eV, something like that. And why is that so important? So usually a monolayer TMD is not actually a monolayer like graphene. It's actually, a monolayer is actually composed of 3 layers, where you have here your transition metal, like molybdenum or tungstenum, between 2 layers of your chalcogenide. So that's why you have the dye here, the Di. So you have 2 layers of, can be sulfur or can be selenites, and then between them we have this kind of, we have those transition metal. If you have a look in the top view, this is the symmetry we see. So it's actually, each point here is actually 1 atom. So you have here the metals, and then you have here the chalcogenides. And interesting is that this is in the representation in the real space. If you go to the reciprocal space, it's just to preserve the hexagon symmetry, and we have this kind of points over here, which is from group theory. I will not go much into details, but the most important points here are actually these ones that we call K and K prime points. And this K and K prime points is exactly where you have the band gap transition in this material. So why is this material interesting? So since we have the transition matter over here, this is actually the d orbitals, right? So actually the d orbitals has a very strong spin orbit coupling. So basically, it has this splitting in the valence and the conduction band, exactly these ones over here, where you actually have, this is occurring in the K and in the K prime point. So basically, you have here, for instance, spin down, spin up, and when you go to the another valley, which is the K prime, it actually inverts the direction of the spin. And we can select this valley or this one, so we can actually select if you want something like this or something like this, using light, just using a circularly polarized filter, a circularly polarized component, and then we can select the K and the K prime point. This is very easy to do in the lab. It's not that hard. It's just try to probe these electronic transitions. Here is actually just to perform some photoluminescence measurements and just try to select. This was actually done a few years ago, I think 2012, I don't recall, from Kin-Fai Mak when he was in Cornell as a postdoc. So what is actually so interesting about this material? So if you combine the spin orbit coupling plus the broken of inversion symmetry, just selecting those values, we can actually have a spin split valley. We can actually have a spin valley locking, and all of this has some remarkable phenomena in the fundamental physics point of view. So one of them is, I'm going to demonstrate it here, is just the Wally-Zeeman effect. So this is why we are interested in TMD. So just for you guys to know what kind of the material and why I'm using that. So how can I probe this? My work is quite simple. I just do one thing. I just have a laser, and the laser inside on the top of the material, and then I just collect some signal. The signal can be photoluminescence, so I can probe the electronic transition, something like that. I can use Raman, so Raman will give me information about the crystal structure through funnels. And then I can have here is SHG, which is second harmonic generation, but I can have nonlinear optics. So I'm getting information about high order susceptibility in this case. And each one of these techniques has its advantage and disadvantage. So I will not go much into details, but I can actually have I can actually use, and I will use those three techniques to try to get information about the material itself. Okay. So to demonstrate the power of optics and the approach that I'm trying to demonstrate, that we can actually have engineer the defect, right? So what we did was quite simple. In collaboration with the Penn State group, they synthesized WSC2. This is the material I have, so it's tungsten and selenite. And we introduced a doped this material with vanadium. All right, and then what we did was quite simple. We want to select just the different values and see what exactly will happens. So we also apply here a magnetic field in the vertical, perpendicular, sorry, to the sample. And just trying to collect the photoluminescence to try to see the electronic transitions, this is actually what we see over here. So this is a considerably high doped WSC2 material with vanadium. And here, for each color here, means just a different magnetic fields. This peak over here is actually the one I mentioned before with the direct band gap. Actually, this is an exciton, for those who want to know the more technical name. This is an exciton, which is a free exciton, actually. And we notice in the lower range of energy here, about 1.6, we see some shoulders, right? These shoulders actually are defect states. So basically it means that we are trapping the excitons in those defects. And where exactly is this defect? Is the impurity that I'm replacing. I'm replacing tungsten atoms by vanadium. So this creates some kind of zero-dimensional defect. And this creates new electronic transition. So this is electronic transition I'm actually observing with the magnetic field. Here on the left and right side, I just have rotating the sample one direction and then rotate, not the sample, sorry, rotating the lights. So using circularly polarized lights through the left and right sides. So that's the only thing I'm doing. And we can see that this peak related with the defect, which is bound exciton, we call it, we see this kind of behavior over here. And on the another direction of the circularly polarized, we just see it goes to another direction. We have as well one feature quite interesting here. You can see it's not so sharp, the peak. So there is also some kind of doping that can be from the substrate, since we use the silicon substrate. So we have the trion. Trion is just electronically charged exciton, okay? So what we notice kind of is, so we just consider the position of this peak as a function of the magnetic field. And what we actually observe here is that the trion, this negatively charged exciton, so this is the peaks considering for one direction, and here is through the another direction. So just the position, tracking the position of this peak over here. And if you take the difference here, peak position energy, right? The difference here of these peaks, we can actually observe this kind of curve. This curve here is actually the Zeeman splitting that I'm observing for this kind of excitonic behavior. And it presents a linear decay like this, a linear behavior. However, it presents a G factor of about 5. This is actually normal for TMDs in general, for pristine. However, if we go, however, if you take a look for the bound exciton, the one related with the defect, we actually observe a 10 times enhancement of the signal. So the G factor is about 52. So basically what we're doing is by introducing vanadium, we are actually creating a magnetic momentum quite intense into the system. So now we have some kind of applications for that. And it's important to emphasize as well, if you take a look, a close-up over here, you can see that this is basically spin, all right? So it seems to be some paramagnetic behavior for this kind of peak. There is a discussion is still in the literature because some people demonstrated it's a ferromagnetic material when you introduce vanadium, but here we are actually seeing a paramagnetic. So there is still this kind of distinction. This work is kind of recent. It's less than 2 years. We published this in small. So think like this. Okay, so I intentionally introduce vanadium. You can see that I'm changing the electronic properties somehow, because now I have the defect bound state. The thing is, I don't know yet about the distribution of the vanadium into the crystal. Okay, I just know that we grow the material and we can see this kind of magnetic properties. So let's go to nonlinear optics now. I want to try to see, try to actually see these electronic transitions as well using another techniques. So, but instead of use WSC2, we use WS2. That's the only difference, but the same methodology, just to change the calculation I. So here we have 3 samples. One, it's a pristine one, no defects. And then another one is a very low concentration of vanadium, and another one has a higher concentration of vanadium. So this is the electronic. So here is the exciton. We can see very nicely for this MOS2. For MOS2, you can see it's about 1.95 in this kind of sample. And then we start to see some small shoulders over here, which is related with the vanadium, the defect. And then when you have a very high concentration, we can see how it is. You can notice here just the red and black spectra is on different points through the sample, and you will understand why I'm demonstrating those two. So we perform a mapping. So we just select this area you can see here, and just for each point here we collect this kind of spectrum, and then we can actually plot this map. We can see this is just the intensity of these peaks, and here is just the energy, which is the position of those peaks. We can see that actually starts to have some kind of this linear here, this line, sorry. And this line is somehow exactly like in the bisector, right? So for instance, if you take a look in this one over here, you can see the line is along the bisector of this triangle, as you can see here. So actually this is kind of interesting. We can see that there is a shifting energy of those peaks, and the intensity also kind of decreases somehow. So we were, okay, what exactly is that? Is there a way to try to demonstrate that somehow? I will not go much into details, but we use basically nonlinear optics called 4-wave mixing. And we just did a scan, so because to take this kind of spectra, this map in here takes quite a long time. So by doing nonlinear optics, we can actually observe that in just a second. We can have this kind of image you can see here. And notice that, I'm not quite sure if you guys can observe, but over here, you can see there is, right, some black line, especially here and here. However, this depends on the excitation energy. So depending on the laser energy I'm actually use, something that was dark actually started to enhance, became bright. So one, there is a clear indication that we are modulating the electronic structure somehow. And we know there is vanadium. We know that this is correlated with vanadium. And if you just take for just tuning the excitation energy of the laser and tracking here, just like this line scans we take in here, just to plot the intensity as a function of the excitation. And for the pristine, fits very nicely. We can see the free exciton here. And then when you go to the highest dopant sample, this is also shown for this one I just didn't present. We can actually see it starts to get a little bit more sharp in here, and there is a new state that appears here. So this is basically demonstrating that we are getting information using, in this case, would be the third order susceptibility. But this is a confirmation that the electronic structure is changing as well, and somehow seems to be in a specific geometry, right? So the next step was, how can I know the chemical cartography? I want to identify all the elements possible, especially in this bisector lines. This work is on archive. This was done by a student of mine, Felipe. He was a student here Now he's in Paris pursuing his doctorate. So as the follow-up now, so I wanted to try to identify if I truly have vanadium and if vanadium is exactly in those lines. So what we did was quite simple. Let's just measure using X-ray. So we went to the synchrotron and used just a X-ray fluorescence. That's all. So this way we are able to quantify and make sure what is the chemical composition of our material. So this is a fluorescence, an X-ray fluorescence spectrum. We can see here some peaks correlated with the emissions of the sulfur, of the vanadium, and of the tungsten. Here is just the excitation. Here is 11 keV, and here is 6 keV. So we are just mapping those peaks. And if you take a look now, I can have a pristine sample, which is something like this. So here we are just observing the L shell of the tungsten, alpha emission, all of them are alpha emissions. Here we have the K shell of the sulfur, and here would be the vanadium. Notice that for a pristine sample, no defects, no vanadium. It's a homogeneous uniform distribution for tungsten and for the sulfur, and of course there is nothing here for the vanadium. However, if you go to a highly doped sample, that's what you get. For the tungsten, for the sulfur, you can see that's still uniform. There was no change. However, there was a reduction, a depletion of the tungsten, specifically in those bisector lines. And the vanadium, it's actually distributed exactly where the tungsten was reduced, exactly in those lines. And intriguing is just to take in a line profile here, like this, across, we can see there is a reduction of the tungsten. This is about 70%, and here is about 33%. So it's proportional, kind of. Of course, it's inside of the error bar. So we are actually, two things we are demonstrating. One, we confirm that we have vanadium. Two, the vanadium wants to stay in that bisector for some reason. Three, we noticed that everything we knew about characterization using conventional optical spectroscopy, and even some electronic microscopy, it was actually just an estimation, was not precise. So if I'm not wrong, the sample is about 4% of WS2 that we actually named it before. However, we can see that there is a very high concentration of vanadium. So we are, for the first time, actually demonstrating the real way to quantify, to determine how much is the concentration of vanadium that we actually introduce into the sample. Okay, so the incorporation peaks has 33%, and it's very, very interesting. So the question was the following. Okay, this is material science, right? So engineering, I can introduce defects, which in this case is the vanadium incorporation. And the next question would be why they want to stay in those bisectors. Makes sense, right? Try to understand. So we are proposing a model to explain this. So it's just a thermodynamics, quite simple, just a diffusion. That's what we are trying to do here. So we are proposing something that we call a desorption growth diffusion model. This is the name you are given. So when you have, when you're growing, synthesize the samples, you have a point, and this point is your nucleation center, basically. And then from those points, from this point, it will expand, and then will form the triangle that we saw, the sample itself. So you're actually considering, you have a growth and a diffusion process competition between them together. So basically, if you're considering, if you have a very center here, and then it started to expanding, so basically, we notice that the vanadium, for some reason, this lines here, the bisector, will act as a sink, where the vanadium wants to stay there first. So in the moment that you have the deposition, you have the vanadium atoms going through the substrate. For some reason, because of the energy, the DFT reveals that you have an energy of about 4 eV lower formation energy in the vacancy. So these lines will act as sinks, kind of trapping the vanadium. So we propose a model that is actually just a convolution. So we use this concentration estimation that we propose. I'm not demonstrating the equation here, but the most important feature is this beta parameter here. So the beta parameter actually in our experiments is kind of around 50, and it indicates that there is a kinetically limited regime for the growth. So basically, beta is proportional to the velocity of the growth, and then you have that it's inversely proportional to the diffusion. So the physical meaning is that your sample, the growth front, is moving so fast that's kind of the vanadium atoms that are actually trapped, initially trapped in those lines, is kind of freeze there. So it's kind of trapped. So the growth is so fast, much faster than the vanadium starts to spread out through the sample itself. I'm not saying that there is no vanadium along the other homogeneous samples, all right? I'm just to say that most of the concentration of the vanadium atoms, because of this competition, because the sample will grow so fast, the growth is much more faster than the diffusion of the vanadium, it takes a little bit more time, so the concentration is there. That's what we are proposing here. And the interesting of this model is that it actually can explain our results quite nicely. No one has done that before, so we are actually the first ones trying to explain how the growth actually works. And we have the experimental evidence for why is that so, right, for different optical techniques, and also explaining using fundamental physics how that is actually occurring into the system. So this is kind of interesting. So it's a competition between the growth and diffusion. So the second part, the third part of the work would be, okay, so I have that. I notice where it is. I know there is electronic change. I can explain why they want to stay there. And just something that's very important, this model here, we can actually use this model based on the parameters that we have to kind of control, to engineer defect, truly a defect engineering. So by changing the time and parameters of your experiment, I can, for instance, control the doping somehow through the process where I could have some dots over here. So for instance, we have the nucleation point, then we could have a 1 point over here, only with the vanadium, and then we stop somehow, and then we continue the growth, then we would have some kind of another point. So it's possible to have a quantum dot defect engineering device using this kind of model. And this is what you're trying to see if it is really possible in our next steps. So moving on, I need to give you a physical. Another thing that we actually notice is that there is a modulation of the funnel. As I mentioned, I used 3 techniques just right. Photoluminescence, Raman to try to see the vibrational modes, and then we have now the nonlinear optics, and of course synchrotron as well. But here is the WS2 doped with vanadium. So we just select this area. So here we have the bisector, and here is like the monolayer itself. So you can see that for a pristine sample, we do not have any kind of defects. So basically, I have two. There is a set of modes. I'm not going into details, but let's pay attention only to. One is the vibration of the modes in the plane, and another one is the vibration out of the plane. Considering the irreducible symmetry, we just call the in-plane vibration as E prime mode, and the out-of-plane vibration as A1 prime mode. That's all. Okay, so in-plane, out-of-plane vibration, that's all. Notice that as we introduce the defects, so measuring now over here, So in the domain interior, so this is the doped sample. So this one here is this spectra here in this point. We can see that there are new features that start to appear. So you have a phono mode over here. We are calling it as J3. And there is another peak over here that's calling J2. So you can see this mode over here when you have this kind of transition method like chalcogenides. The defect band is this guy over here. So this is an indication that we truly have the introduction of defects into the lattice as well. Okay. So the interesting point here, so it seems that we have a formation of some kind of VS2 material. Okay, so we have the WS2, but we have also the VS2. And the vanadium is much lighter than the tungsten, right? So you would expect actually to have some kind of comprehensive tensile stress. However, as I'm going to demonstrate you, is that all the samples, especially in these bisectoral lines, demonstrate that we have a tensile kind of strain. And the tensile kind of strain that we observe over here is about 0.7%. Okay, so actually the introduction of the vanadium also modulates the vibrational modes, and somehow you have your material is kind of plain. However, you have an uplifting. So it's like a wrinkle, you know? So exactly where you have this bisectoral lines over here. So this is just a plot we did considering different points to try to map it out. So this is just the position of this mode as a function of this mode, and using this equations here that is already well established in the literature, we can actually verify a competition between stress and strain, and actually as well doping in the material system. So this is quite a remarkable. So it's like you have the material, you have the uplifting. So basically now I have zero-dimensional defects actually creating some kind of topographical morphology that can be considered one-dimensional. And I can make a device using that. So this is next step for applications. So because of the time, I think I still have a little bit. Let me change a little bit the topic now. Is it still defects? I've just changed the material. That's all. Okay. So we use TMDs. TMDs was something kind of hot topic. So we know how to do that well. So why we know TMD well? People in Penn State were one of the first ones to synthesize that through chemical vapor deposition. So kind of understand how that works. However, we know how well we can grow graphene, right? Graphene is well established as well. There is only one problem when you are working with graphene and you wanted to quantify defects, is that we only know how to characterize and account defects for one layer, monolayer graphene. That's all. Okay? And one of the issues that we have, especially if you are thinking about industry, is that we need to quantify. We don't have any model that can quantify defects and different number of layers in the system. Doesn't matter if it is graphene or if it is any kind of TMD materials. We do not have that. We just know how to count defects for monolayers. Okay? So the next step was, is it possible for us to try to synthesize 2D material with different number of layers and try to account defects? So that's what we start to think. And then what we did, okay, let's work with graphene because we know how graphene works and the spectrum is much more simpler than TMDs. So this is in collaboration with Korea and Japan. So basically what we did was kind of follow. We grow the graphite using boric acid to introduce it, to replace carbon atoms by boron. That's all. So we will have a boron-doped graphene system, okay? So, however, what we grow is not monolayer samples, it's a crystal. And then we get this crystal and exfoliate it then. By exfoliating, so this is optical microscopy images. Here we have a different number of layers. Not quite sure if you guys can observe it there, but here, very thin layers representing graphene, okay? And it does work because the boron diffuses about 100 microns from the surface. So it's deep, quite deep into the crystal that we synthesize. So we can just exfoliate that. And it's interesting that different points here on this material and, on this flake, we'll have different boron concentration. So when I say boron concentration means defects, same thing. Now I'm just replacing carbon by boron, that's all. So it's a zero-dimensional as well. However, this we didn't look much into how distribution it is. We just want a metric way to quantify defects in different number of layers, that's all. So we propose that, and for monolayer graphene, the defect band is this one over here. So if you have a peak over here, you can see that in this direction, this intensity of this mode starts to increases. This is an indication that we have defects into the lattice. The same thing occurs for bilayer graphene over here. So basically, those two peaks, so the D band, we call it D band, when you take the intensity of the D band as a function of the 2D or even the G band, this band over here is actually the in-plane vibrational modes of the graphene. We can actually account defects using that. However, we cannot do that when you have few layers graphene systems. Because when you're measuring the Raman spectra, for instance, the scatter light will have different signals, right? Because of the thickness. It's like one layer will have more enhanced maybe than the top, than the lower one, basically. So the intensity is kind of, it's not a good metric system for to do that. So we propose something very differently, and it is quite simple. It's over here. Instead of considering the intensity and position, we consider the integrated area of this band over here, we call 2D, over normalized, can think like that, by the integrated area of the in-plane mode, which is called G band, as a function of this integrated area of this band normalized by this one over here. So what we actually get is this kind of mapping here, where you have in this direction here means you can see different colors, right? Each colors represents different number of layers. So in this direction here we have the layer count, the number of layers that we have into the system. And in this direction here, what you have is the amount of defect density. So here is increasing, in this direction increases. So we observed that we have this kind of behavior for this system. And it's quite interesting, it's because, for instance, if I keep the amount of defect density constant and also the number of layer constant, what I get is like a point, all right? So it's very well concentrated, localized. If I keep the sample thickness constant, in this case it's a monolayer graphene, but we are changing the concentration of the defects, we have this kind of behavior over here. If you are actually now keeping constant the defect density, but change the number of layers, this is the kind of spectra that we are, this is the kind of graph that we are actually observing. So basically what we are actually doing is kind of a graphene atlas for defect quantifications in graphene system, okay? This is work with for graphene at the moment, all right? This is just a calculation to corroborate with our experimental evidence. This was done by Pedro Venezuela. He helped us with that one. So all the results that I mentioned here can be summarized in this data over here. So this data is kind of, it's similar to the Catori plot we have for nanotubes. So basically now, if you take a look in this graph over here, if you know the amount of defects and you know which number of layer you have, one or another, you will know exactly where your the amount of defects, number of layer, and everything you need to know, it's here right now. So we are kind of have a universal metrology for point defects in graphene, and this has never been done before. Just so, before you ask, is this true? Yeah, it is. Here is our 10,000 spectra data points that we actually took to analyze this. It's 10,000 data points. So yeah, we are kind of sure. So just so for you know, when you have the change here is LD or ND, depends on, usually we, in graphene system, we like to quantify defects using parameter LD and ND, which is basically well known by Cansado's work. So basically, this slope here is actually giving us the information that we truly needed for the amount of defects that we truly have into the system. So this is quite nice. We actually have a way to quantify defects universally in graphene. This work is actually under review right now, but you can read it on arXiv. But this is like applications, right? It's quantification. So we are moving on to the next step is the following. Okay, how the electronic band structure are actually changing and how I can probe that. For graphene system, the best way to try to probe the electronic structure, because it's linear for monolayer graphene, is Raman spectroscopy. Because basically, how we can map that, if I just change tune and excitation energy, you can see that the D band actually changes its position, right? It's a linear dispersion. However, you can quite notice here, so there is a modulation in the electronic band structure, because this band and this band is actually shifting, right? This is for like a considerably low concentration, and this would be higher concentration of borons, just to demonstrate that we have the same behavior. Only the intensities, of course, it's changing. And also notice that the shift, the downshift that we have for the red laser over here, which is 633 nanometers, is kind of more shifted than the other ones. And I'm kind of explain a little bit why. If you take a look in pristine samples, for pristine samples, this band over here, this 2D band, is actually a very well-defined feature, this peak. So I can just fit this one, consider one Lorentzian peak. If I go to the bilayer, I can actually see fit this band for considering 4 peaks. However, so why I have 4 features? Because I have the inter and intra-layer interaction in bilayer graphene systems. So considering all the hopping terms that I can have for the electron here, I can actually have 4 features. However, for the doped samples, considering for this wavelength over here, 2.3, for bilayer, I don't have 4 peaks. I have actually 6 peaks. So we are not so sure why we have that. We don't know. It's kind of basically we have a new scattering channels for the electron because of the defect that we are actually incorporating into the lattice. And this is actually still ongoing. This is it's being investigated by a student of mine. So we are still trying to figure out what is happening. And it's not so easy because DFT calculations actually demonstrate. So this is a band, this is DFT calculation from the band structure for, this is a pristine bilayer graphene. We can see here in the K point over here, you see those 4 bands. These 4 bands are actually correlated with those transitions that you can see here. So the Fermi level is actually 0, okay? And when you have a higher concentration of defects, it becomes something like this. So basically, this top band over here, this range, actually comes quite a little higher. This lower one here in the conduction band starts to kind of split in two. We have one minimum here and another minimum over here. And then those 2 bands over here in the valence band kind of shifts, as you can see here. So we are actually having some new scattering channels, but we are still investigating how is the conservation of the phonon in this kind of situation. We are still calculating that and try to figure out, corroborate this theory, this calculation with the experimental results as well. Another point that I mentioned is the following. So as you can see here, this one is kind of low, right, compared to the other ones. In graphene, the direct point is basically, if it is a linear, if it is monolayer graphene, this one should be linear here. And the surface, right, the direct surface would be just 1 point. When you're getting closer to the K point, you have something that we call Conn anomaly. So something is actually happening there. So we were interested into, okay, so if you are introducing boron, we are modulating the electronic band structure, so probably a gap will be opening. This is also demonstrated by DFT. I'm not showing here the monolayer calculation though. However, so we said, okay, how can we probe that experimentally? So is it possible for us to try to go in lower in energy, below 1 eV at least? So what we did was to perform scattering type near field optical microscopy using this technique called SNO. So basically, this is also done in the synchrotron at Sandepen. So basically what we do, we just use a tip, and this tip here is about to give us a resolution of about, can be between 10 to 25 nanometer resolution. So we are getting very, very close in energy of the K point. And we have amplification here of the magnetic field because of the tip. So the one we use, it's gold, and the one, I think the resolution is about 20 or 25 nanometer, I do not recall properly. And what we did is just to try to collect an infrared signal, that's all. So this is a synchrotron measurement. So this is kind of the peak that we are actually measuring. This peak over here is because of the silicon substrate. So we are using silicon. So silicon has resonance in this range of energy. However, if you take a look here, we can actually see that the intensity is changing, right? When you have monolayers and bilayers. So this is kind of the samples we have. Maybe it's not quite clear, but over here is the silicon substrate. Over here and over here, it's like the monolayer, and over here, here is the edge of the bilayer sample. So what we notice are two things. One, the intensity is changing. So the intensity variation means that we are doping the material. Another thing that we have, there seems to be a feature over here, about 800, 850, something like that. And there is another feature showing up around here. And we are not quite so sure what that is, but could be plasmonic effect that we actually having into the system. So this is the mapping. So we have this one collected for a specific line. So we are just trying to, we fix the laser. Now we are using a laser and fixing its energy exactly at this feature over here. We are seeing the left side is the amplitude, and on the right side is the phase. So basically, here is the monolayer, here is bilayer, and this is the substrate. So you can see here the resolution, it's 1 micron, the size of the image in here. Well, the sample was damaged. That happens because it's a tip, right? So, okay, that occurred overnight, so I wasn't in the lab checking that. But you can see here it's a little bit difficult to try to observe some kind of features that's actually occurring, right? However, the phase starts to show something over here at the edge, which could be something expected because of the doping or some kind of vacancies. However, for the edge of the bilayer, you can see some stripes over here. So to try to better see what is happening here, this is just the derivative of this image here. And now we start to see two lines appearing over here. And even for the monolayer, we can also observe there is two lines over here. So there are some stripes here, here, and over here. So you are not seeing this edge being enhanced just because of the direction of the derivative we took at this image. Something that has been reported is that this is graphene, where you have a gate. So it's a pristine graphene, and just make a device and apply a gate. And they were able to observe some very nice features that starts to show up here, which are actually plasmons, because we are doping the material because of the voltage that you are applying. So basically what we are observing, we believe to be observing our result, is that we have some plasmonic effect as well that are naturally appearing in the material because we doped the material with with boron. And we are trying to improve now these measurements as well. We are trying to get a better resolution of this one. We are probably going there in this year to perform this kind of measurements. And if we also considering some kind of line profile over here, if I'm not wrong. That's how he did it. And we are just trying to map the band structure to this is known band structure mapping, something like that. We can see that for the silicon and for the monolayer over here, we have those enhancements. So basically because of the substrate itself. However, for bilayer, that's where the things are starting to get interesting, because we see there seems to be some transitions over here. There is also in this range here and around this range over here. And you can see that we are very, very close in energy. We are measuring milli EV here. So it's not 1.9 EV anymore. So you're very close to the direct con over there. So you're probably something between, perhaps closer to the possible band gap in the material. We are still investigating that, so it's still ongoing. This is done by a doctorate student of mine. So hopefully this year we will have a better understanding what's going on in this kind of measurements here. So I think I'm on time. So the take-home message is quite simple. Defect is not a bad thing to have if you can actually control them. So if you can engineer the defect in a way that you can modulate the electronic band structure, even for some kind of magnetic property into the material, so we can do that. And even if you are able to control how is the growth velocity and the diffusion of the atoms that you are actually incorporating into the lattice, we can have different defect engineering devices. And this is what we want to do in applications. I didn't demonstrate here, but we published a paper this month in I think it's ACS Nanomedicine, something like that, where we actually use another TMD called MAOS2 as a sensor for DNA nucleobases. So it's a biosensor using these defects in 2D materials. So the message is, as long as you can control, we don't want anymore just to characterize. We know how to do that quite well. Now we wanted to engineer into defects for some applications. So the symmetry driving here is because we are breaking the symmetry through the lattice, introducing some kind of atoms in the material. We can have a deterministic atomic engineering dopant distribution, because now we have a model to try to predict how we can control that. We can actually observe that the higher concentration of defects, at least in TMDs, they act as localized stress concentrators. And also, we can actually have a graphene atlas to quantify defects in graphene materials in general. And finally, we are trying to go beyond the diffraction limit, right, which is very close to the 20 nanometer scale, to try to get much closer to the electronic transitions of the material. So this is the kind of one of the directions that I work with. So I just select one topic, was one specific type of defect. Of course, this work could not be done all by me. As you can see, I use different techniques, different samples. I have a lot of collaborators, experimentally, from theory as well. So I would like to thank all the optical spectroscopy guys as well. So especially to Mallard and Pimenta, Cristiana as well. Fred, that is doing this performing the experiment of the X or F measurements as well, that one for the magnetic one. Felipe, now he also did this experiments with us, considering the four-wave mixing. It was his master's dissertation. Now he's in Paris. And everyone here, like Tony Hines, Luis, now he was at MIT and Harvard. Now he is a professor in USP this year. Also, coming from MIT, Patrick, he's not in Cornell anymore, but he came back. He went back to Europe, and Phi. So these are all the guys from optics that I'm always discussing all the time. From the synthesis, especially Mauricio Terrones and Fujisawa-san, they are the ones that do the STM imaging and the sample preparation as well. Also, Yulei from China, now we are getting more collaboration with applications as sensors using materials. And also, well, as you can see, I have a very large list, I think just some of them. And from DFT, I would like to especially thank Mateus from UFOP, Shashan from UFMG. They are the ones that did all the calculations I show in this presentation, as well Mario, Pedro also did the calculations considering for the graphene. And Iwan Shi and Craspi, I still have collaborations with them, and the SPM measurement, the scanning probe microscopy, which is basically Ana and Bernardo that are actually doing. So experimentalists, because we have this different set of techniques that we are trying to do today, all of them actually contributed to this work. So just like to thank all of them over here as well, that somehow it's supporting the research. And well, that's it. Thank you so much for your time.
Okay, thanks, Bruno, for the very nice talk.
Thank you.
Let's open for questions.
So I have two questions. The first one is really silly. So when you doping your tungstenium with vanadium, you are just breaking the lattice symmetry, but you're not changing, for example, the spin orbit coupling, or you're not interested in this kind of thing, right?
Well, we are. I just didn't show here.
Okay.
Because this idea was just to demonstrate that we can actually engineering, right, the facts and see that they are actually modifying the electronic, that somehow the properties of the material. But yes, we didn't actually pay too much attention on how the spin orbit coupling would actually change, because the vanadium is lighter than the tungsten. We didn't actually go into that direction. And here is the thing: we are not quite sure if the symmetry is still 2H hexagon or hexagonal, or there is another kind of phase, because you have the bonding there, which is 1T phase we call, which is a lower symmetry than the hexagon one. So we are still trying to figure that out, and it's still a discussion in the literature. We believe to be 2H. The STM results also demonstrate to be 2H. However, maybe it's because of the region that we are measuring, or another one I didn't show here, but this is a discussion we're having this week. And yeah, for now, after we define and decide which symmetry it is, then we can actually go to another part of the work. The people from UFOP, Mateus, they are doing the DFT calculations considering the modulation of the band structure, but I'm not quite sure if he's looking into details about the orbitals as well. But I think there is no change if it is 2H.
Okay.
Yeah.
I don't know if it's easy to do this, but if you try to change the vanadium for example, cerium with the spin orbit coupling so high, maybe the defect could change?
Probably will. Well, there is some considerations we need to do when you are actually trying to synthesize the material. So we need to, I didn't consider that. But of course, if you take, we could take a look on that. The only thing I can guarantee you is, well, I mentioned that vanadium is there in that bisector, right? However, when you're synthesizing pristine samples, they are actually not 100% pure, right? It's actually 99.99%. It's different because work we did, I think 4 years ago, using nonlinear optics, we demonstrate there is actually a lot of materials as well, metal ones, that are actually contributing as well. They prefer to stay in that bisector, so maybe something would be similar. I don't think it maybe in the mechanical way, perhaps, or maybe the deposition will be the same, where they want to stay, but I don't know how the electronic would actually change, though. Yeah, thank you.
Okay, sorry, I will just ask one more question.
Sure.
When you show the graphene atlas, when there are monolayers of graphene, And when you mentioned this in the beginning of the talk, if you rotate, you have the Moiré physics and this kind of thing. So you can combine this type of defects effect with the Moiré physics to see how the defects affect the superconductivity, have ferrophysics and this kind of thing.
Next step.
Okay, thank you.
So what I can tell you is, one thing is just go back a little bit in here so I can answer your question properly. So it's because I didn't show here, but you can, I didn't mention, but if you pay attention, even for graphene itself, the intensity of this band kind of disappears, right? For higher concentration, the 2D band intensity disappears. So this is an intervalley where the phonon is being scattered from 1K to K prime valley, and then come back. So we have two phonons. It's in-plane TO phonons, basically, transversal optical phonons. So one thing that we are trying to do first is to make a device we can just apply some gates and try to see if you can recover this band. And after that, we are planning to do this the Moiré physics. However, it's not that easy because, as you know, it's 1.1 degree angle, right? That's a specific. If it's 0.2 or 0.3 or 1, this will not work at all. So it's not so easy to try to do this kind of stacking. So we are trying to discuss this with collaborators at UFMG, and maybe we are going to send them the samples to try to synthesize, because it's more transport side to try to do these measurements. From the physics point of view, maybe just from the optics point of view, two things I could try to see would be trying to do some nonlinear measurements, try to see the phonons using nonlinear optics to try to map some kind of Raman scattering. And another point would be, if you're measuring conventional Raman, perhaps some new phonon may appear. Do we do the Moiré superlattice? Yeah, that's what I could think right now.
Thank you.
Yeah.
Are there more questions?
Bruno, is a perhaps a naive question. It's not my field. So, how doping could change the absorption measurements in those materials, or any defects in general?
So basically, boron, for instance, is a p-type doping that we have. So the electron now it's above the calculation demonstrates above the energy, the Fermi energy, and everything there will change how the electron will be scattered. We don't know how is the scattering channels. So for instance, we could use this sample as a sensor, right? Because now we have more charged particles there. So maybe that will enhance the intensity of some kind of molecule, for instance. So in the physics point of view, the doping just provides us our better sensor, or maybe in the absorption, it would be similar to PR, perhaps, to the photoluminescence spectrum, because we would see some states that are correlated with this trapping, this defect bound exciton, actually. However, to think, CVD is not so good sometimes when you're doing this kind of measurements, because it's easier to go to lower temperature, like a 4K or something like that. And when you decrease the temperature, the excitons, the peaks start to be more sharper, right? And they are sharper peaks. However, sometimes you see a lot of features that could be from some kind of, we didn't know was there because of the deposition during the growth. So sometimes it's a little bit more tricky. I did this kind of measurements for CVD before, I think a few years ago, and it's not so easy to figure out everything that's happening, because it's a little bit of a mess. So you have, whether it or not, we still need to improve this kind of synthesis to try to observe. But in that sense, it's just doping. We'll just shift the peak's position, and then we'll have a new kind of, if you're in incorporation, so we will see some defect-related states. That's basically it. Yeah. That can, yeah. Usually it's lower energy, but that will depend on. So we observe in the Raman, right? Raman was actually a downshift, a redshift, and should be a blue shift because of the vanadium introduction. So maybe even the lattice itself, because the way they are changing, the modulation of the electronic cloud, that would be actually affected. So not so sure if it would be higher, lower, so it will depend on the kind of doping you're actually doing, yeah.
More questions? Well, I have a small one.
Sure.
Can you just maybe say a few words? I don't know if I missed it, about the K and K prime points when you showed the lattice.
So the first one, I think?
Yes, right in the beginning.
From the valley, this one?
Yes.
Yeah.
How can you see that from, I don't know, group theory stuff that you mentioned, the reciprocal lattice?
So you mean from well, so this is the K gamma M points. They are actually high symmetry points that we have in the D3H or D6H symmetry, basically. This is from the group theory. So there is all demonstrated which are the paths. This is well established in solid state physics. Mm-hmm. So basically what we wanted to do when you are doing some kind of calculations, I'm sorry, again, I'm not from theory side. So however, everything we need to know is what is happening between gamma, M, and K. So you see there is a rectangular, right, a triangle over here. Mm-hmm. So everything that can be calculated here, we will know that will happen for the whole lattice. Something similar to, let's see if maybe that one where I should demonstrate the band structure. Something like this. So you can see here is just again in one direction from gamma, M, K, and gamma again.
Oh, I see.
So here we know the positions because these are vectors. So we know exactly the position of each one of them in the reciprocal space. And doing so, when you do the calculation, I don't know how exactly this is performed, honestly. We can see that most of the physics is because the atoms are actually here, right, in the K and the K prime, you can observe where you have the if it is semiconductors and metallic and so on for this, at least for this symmetry. One thing I didn't mention is that you have the K and the K prime points. So each one of them, even for graphene, it's like we are actually having different atoms because they have sublattice here, right? So that's why you can see it's green and yellow. Although it's carbon here, you see this different color because we have different sublattice. Because of the hexagonal symmetry. So, and also to go from one valley to another valley is you have the time reversal symmetry as well here involved. So even when I try to select, for instance, intermediate spins, I need to consider that when doing the measurements. But we already know that, so it's well established because this has been investigated since 2010. So for TMDs and for graphene even before. So this is already well established in the literature. So everything we wanted to see is what is happening, how the electron, in this case, what I want to understand is how is the scattering mechanism or channels, pathways, considering the electron from here to here. If you are considering, for instance, phonons, all the phonons, for instance, the 2D band, the D band, they are actually phonons involving scattering from K to K prime points. And this one here, it's just the in-plane vibrational modes of the carbons. So it can be in the X and Y directions. So everything depends. We can combine those things with DFT to try to figure out what's happening to the system. Basically that.
Okay, thanks.
Okay, thanks, Mars.
More questions? Well, if not, let's thank Bruno again.
Thank you. Thank you all.